The beautiful planet Earth, our home. Covered by oceans, the watery cradle where life began. But now, human activities threaten our birthplace. Our fossil fuel-based society emits vast amounts of carbon dioxide each year. And as carbon dioxide increases in the air, it also builds up in Earth's oceans, driving up acidity and affecting all who rely on those oceans. The Royal Society, the UK's preeminent scientific organization, tells us the oceans are acting as an important carbon sink, absorbing 2 billion metric tons of carbon per year, more than they are releasing into the atmosphere. This is small in comparison to the amount of carbon that is cycled between different reservoirs, but is a significant proportion of the 6 billion metric tons of carbon each year released by human activity. The oceans and the life they support contain about 38 trillion metric tons of carbon, more than triple the amount contained in fossil fuel deposits, and over 50 times more than is in the atmosphere. Carbon dioxide exchange is a two-way process, with the oceans and atmosphere absorbing and releasing CO2. A decrease in the amount of CO2 absorbed by the oceans will mean that relatively more CO2 will stay in the atmosphere. Only the near surface waters, or surface layers of the oceans, are well mixed and so in close contact with the atmosphere. However, mixing the deep waters is much slower and takes place on timescales of several hundred years or more. Most of the biological activity in the oceans and all of the photosynthesis takes place in the near surface waters through which sunlight penetrates. The Royal Society recommends that all possible approaches be considered to prevent CO2 reaching the atmosphere. No option that can make a significant contribution should be dismissed. Well, since carbon dioxide is the backbone of photosynthesis and thus life, what if that CO2 could drive growth of algae and other ocean life in the sunlight-rich surface waters? In 2005, the U.S. Department of Energy produced a biofuels report known as the Billion-Ton Study. The U.S. government hopes we will grow enough biofuel to cut fossil use by 30%. Yet growing fuel at this scale will take tremendous resources. On the plus side, the U.S. probably has the sunlight, rainfall, and land to achieve this goal. But plants also need potassium, nitrogen, and other minerals, and here the outlook is not so optimistic. The U.S. Geological Survey estimates that of all the nutrients used today to grow our food and feed, phosphorus is in the most limited supply. If they're correct, the U.S. has less than 40 years of economically mineable phosphorus within our borders. Worse yet, unlike the nitrogen fertilizer we can make from the atmosphere, there is no easy way to replenish phosphorus. And if we ask farmers to also grow our fuel, the phosphorus outlook will get far worse. A recent peer-reviewed paper estimates that achieving the 30% goal mentioned before would require the U.S. to use more than 5 times as much fertilizer as we do now. In other words, if we grow significant amounts of biofuel, our phosphorus reserves might last only a few years. So, if we want to slow CO2 buildup by switching to biofuels, where will we get the phosphorus? In the years since World War II, farm yields per acre have exploded, tripling or better for many crops. A major factor has been the aggressive use of fertilizers applied to crops, washed off by rains and irrigation, and carried by our rivers to the sea, where they eventually settle into the depths. The deep ocean is rich in these life-giving minerals, but without sunlight, virtually nothing grows. What if we could tap into this bounty of nutrients? And if upper ocean carbon dioxide is plentiful, what if these are mixed together to create a bounty of marine life? The seas are mixed by several forces. Celestial gravity creates tides, while the sun's warmth drives the wind and waves. Earth's largest storms, the hurricanes and cyclones, are the pinnacle of this warmth-driven mixing. But more than 99% of a hurricane's energy stays in the atmosphere. Thus, even these massive storms add surprisingly little energy to the churning of the seas. Over 50 years ago, Charles Darwin's grandson proposed that the swimming of animals could be a major factor in the mixing of ocean waters. Since then, further work by Walter Munk at Scripps, John DeBerry at Caltech, and many other scientists has confirmed that ocean mixing by creatures, both large and small, could be equal to or even more than the mixing caused by winds or tides. Even more importantly, animals provide much of the vertical mixing in the ocean. Some tunas and whales can dive down 5,000 feet and will drag back a surprising amount of nutrient-rich water. Smaller creatures like krill also play a role. They cause significant mixing because they have large surface areas for their size. So what if there aren't enough fish? What if one reason for the carbon dioxide buildup in the surface layer is that there aren't enough animals to vertically mix the ocean? For centuries, humans have harvested the seas. But the United Nations estimates that in the last 50 years, aggressive fishing has driven many major fisheries into decline. Now we are learning to manage our fisheries better, so rebounding fish populations will restore some of the vertical mixing. But what if we could find another way to bring deep nutrients to the surface? Well, some of the most productive parts of the oceans are where currents naturally bring nutrients from the depths. Notable examples are the west coast of South America and the North Atlantic's Grand Banks. What if the key to ocean health would be to replicate this and create upwellings? In recent years, Lester Brown and others have proposed Plan B to help rebalance our impact on the planet. What if we add a Plan C, a plan to induce upwelling to grow algae and fish? This approach could absorb carbon dioxide, slow ocean acidification, and help feed the world's growing population. We invite you to visit www.earthplanc.com and tell us what you think.